Okay, so this is a theory, and so then we have to do some experiments to see if this is true. And this is the most common experiment. In real life, this is the ground. But I want it to look like our experiment with the truck. Okay, so you get a cylinder of concrete, you embed the bar into your cylinder and you pull it out. Okay, and then what you do is you put strain gauges on the bar, and that's like measuring how much force is in the rope, and this is the total force. Okay, and so in our little tug of war experiment, it was going up 50 with each person, like this. And so the slope was 50, 50, not 15. That's weird how you can write something that sounds like what you said. 50 per person. What we want to know is how many pounds per foot. That would be the slope. And so the slope of this, if you take the slope of that, that's that bond stress we're talking about, that mu. And this is how much you can hold per foot. That's the definition of slope, right? Change per foot. And so if you take here, zero slope, steep slope, this is the slope, and you get the bond stress. And so you could calculate mu. It's kind of weird. It's not constant. And so it does not look like this. It looks like this. But, and everybody who measures development length or bond strength, they do some kind of experiment like this. But this is an unrealistic experiment because this concrete is in compression, right? That's not realistic. In a beam, like our beam, the concrete is in tension. That's the whole point. The bars are in the concrete only where the concrete's in tension. And this actually gives unrealistically high bond stress, because when you pull on that bar, you compress the concrete and the concrete tightens on the bar. So if you've ever done those games where there's this tube, you put your fingers in there and then you pull on it and your fingers get stuck, it's similar to that. So we need some kind of experiment where the concrete's in tension. And coincidentally, a buddy of mine from Hawaii who went to University of Washington before I did, this was his master's thesis. So he did this actually. And we all made fun of him that he was testing concrete ropes. But he made these long things of concrete embedded with a bar, and he'd pull it, and this is what would happen. And so how the stresses change, there's only stress in the parts of the concrete that don't crack, like this. And the bond stress is actually much, much lower. Okay? And so the bond stress in the beam is very similar to this. Well, that is just based on our, this little theory that we did with like the tug of war. But in real life, the bars are not smooth like that. The bars have ribs on them, and I've idealized them in this drawing here. And so when you pull on this, rib here, so the rib here is pushing against the concrete. Okay. Oop, what did I do? Uh-oh. I've killed my notability. It won't work. I can't write. Okay, I might have to stop the video here and restart it. we've been going long anyway because I can't move the slide. And I'm back. I don't know what happened. I had to quit Notability and come back. Back to what we were talking about. Our bars are not actually smooth. They have ribs on them. And I've idealized them with this drawing here. And so when you pull on the bar, on this surface here, let me try and highlight it. On this surface here, it's going to react against the concrete like this. Okay, so again, Newton's second law, equal and opposite reactions. Okay, so you're going to pull the bar out and it's pushing on the concrete. Okay, the concrete pushes on the bar pushes on the concrete. And let's look at this a little more carefully. So if you take this reaction here and you break it up into its components, let me try that again. So if you take this component here, that reaction there, and break it up into its components, the key thing is that there are these equal and opposite vertical reactions, and what they're doing is they're trying to split the concrete apart. It's not that hard to think about. This here is acting like a wedge, and you're pushing this wedge into the concrete, and what it's doing when you pull on that, it's wedging the concrete apart. And that's just one bar. And when you have lots of bars and it's going to wedge that up and that down, if they're really close together, if you have lots of bars, this can happen. You can split the bottom, you can delaminate the bottom of the beam off of the top of the beam, and then you've lost all your grip on the bars, and the bars will just slip out. And so this really does affect, it has nothing to do with that derivation we did with the tug of war. This drastically affects the grip strength. If you pop the bottom of the beam off because of this wedging action on the bars, you'll lose all your grip. And so here it is blown up. And so this is what we're trying to stop. You want to stop the bottom, okay, from ripping off of the top. And this is another benefit of having stirrups. Let me make this fatter. Okay. I'm drawing a stirrup here. So there's our stirrup. And if you have the stirrup, it will hold the bottom of the beam onto the top of the beam, and it stops it from splitting apart. And so stirrups, this is a really weird concept, stirrups increase the grip of the concrete on the bars because it prevents this slipping. So keep that in mind. Okay, so here we go, bars in tension. How do we figure out this development length? And we went over, quote unquote, the theory, and it's very complicated. And so once again, we have something phenomenological. Basically, it's an experiment. We had to do an experiment to figure it out. And this right here is our development length equation. Let me go through this, walk you through this. This is the development length, okay. Oop, let me have to make this not so wide. This is the development length. And this equation happens to be in terms of the diameter of the bar. So do not forget, after you calculate this, to get the real development length, you have to multiply by the diameter of your bar, okay? So this number on the right-hand side has no units. Think of it as how many bar diameters do I have to embed the bar? So if the number comes out 30, then 30 bar diameters is how much you have to embed the bar. Okay. This here, that's the confinement and cover factor. If you have a lot of concrete below the bars, if the bars are spaced far apart, or if you have stirrups, all those things will help you not pop the bottom of the concrete off of the beam. Okay, we'll talk about exactly what all those variables mean later. In fact, all of these, there's a separate slide. Okay, right here. Psi sub t, that's the rebar location factor, and T stands for top. When you were in 3210, and if you had a really high slump and you made your cylinders, did you notice that like water floated to the top of your concrete? And what was happening is water, air, and sand migrate towards, well, water and air migrate toward the top, and the aggregate, and not so much the sand, but the aggregate are migrating towards the bottom of the cylinder before the concrete sets. What happens is that the concrete on the top is weaker than the concrete at the bottom. Now, you need to have at least 12 inches deep concrete for this to happen, but it does happen. This next one here, psi sub E. E stands for epoxy. Rebar rusts, and that is bad. And one strategy to prevent rusting is to paint the outside of the bar with epoxy, and typically it's green, so we call it green bar or epoxy bar. And but this epoxy coating is slippery, and you do have less grip. It's like trying to play tug of war with a steel bar, a smooth steel bar, rather than a rope. At least a rope you can grip. And remember, we talked about how if a bar is bigger, it's harder to get a good grip. That's the size factor there. That's different than the diameter on the left-hand side of this equation. Okay. Obviously, the stronger the steel, it takes more force to break, and thus you have to embed the bar longer. So higher strength concrete, okay, I mean higher strength steel requires a longer embedment length because you have to pull harder to break it. And remember, the development length is the length to embed the bar before you break the bar. And of course, the concrete strength plays into this, because the stronger the concrete, the better you can grip it, right? And so it's in the denominator: stronger grip, shorter development length. And the reason for the square root is because what we're worried about is splitting the concrete, and that you lose your grip, and splitting is related to tensile strength. And remember that tensile strength is correlated to the square root of the compressive strength. And let me remind you again, anytime you see a square root of F prime C in this class, and we're using English units, the F prime C has to be in PSI, which means that the Fy has to be in PSI. Okay, this is the development length equation. This video is getting a little long, so I'll stop here, and in the next video, we'll go over each of these factors in turn.